Suppose you have a set of indivisible objects. Now we've seen that it may not be possible to find an allocation that is both envy-free and Pareto efficient. In this lecture, we're going to consider a situation in which there does exist a unique envy-free and Pareto efficient allocation. However, we're going to see that this allocation does not satisfy a number of other desirable principles. The example we're going to discuss comes from this paper, Paradoxes of Fair Division by Brams, Edelman, and Fishburne. So here's the example. Here's the situation. We have three individuals, Anne, Bob, and Kath, and there are 6 objects that need to be distributed among Anne, Bob, and Kath. Now, I've listed here the individual's preferences, strict preference relations over these objects. So Anne strictly prefers object 1 over object 2. So she strictly prefers getting object 1 over getting object 2. And she strictly prefers object 2 over object 3, and so on. So these are the agent's preferences over the objects. Now we can ask, how can we fairly divide these objects among Anne, Bob, and Kath? Well, it turns out that there are 3 efficient divisions. Now what this notation means, I'm going to drop the set notation. This means that Anne receives objects 1 and 2, Bob receives objects 5 and 6, and Kath receives the objects 3 and 4. Just to keep the notation down, I'm going to write that very succinctly as the sequence consisting of 1, 2, followed by 5, 6, followed by 3, 4. So it's all of these listed. Anne's allocation, Bob's allocation, then Kath's allocation. All right, so this allocation, Anne receiving 1, 2, Bob receiving objects 5 and 6, and Kath receiving objects 3 and 4 is Pareto efficient. There's no other allocation that dominates this allocation. And that's not too hard to see because note, both Anne and Bob receive their top 2 choices. So there's no way to move to a different allocation without hurting Anne and Bob, without taking away some utility from Anne and Bob. The next allocation is Anne receives the same, her top 2 choices. Bob now receives his top choice and the second to last choice. And Kath receives her top 2 choices. Again, since both Anne and Kath receive their top 2 choices, there's no way to improve Bob without hurting Anne and Kath. So this is also Pareto efficient. Finally, we have the allocation where Anne receives her first and fourth choice, Bob receives his first and third choice, and Anne receives her top 2 choices. And this allocation also is Pareto efficient. To see that, note that in order to improve Bob's allocation, we have to give Kath's second favorite choice to Bob. But that would create an allocation that is strictly worse for Kath. In order to improve Anne's allocation, we would have to give item 2, either item 2 to Anne or item 3 to Anne. Both of those moves would create an allocation that is strictly worse for either Bob or Kath. So these divisions are Pareto efficient. It takes a bit more work to prove that these are the only efficient divisions, but for now you can just trust me that these are the only efficient divisions. The only envy-free and efficient division is the last allocation, where Anne receives objects 1 and 4, Bob receives objects 2 and 5, and Kath receives objects 3 and 6. To see that, note that consider this efficient division. In this division, the claim is that Kath may envy Bob. It's not guaranteed that Kath envies Bob, but it's possible that she envies Bob. It's going to depend on whether or not she would be happier with her second and third favorite object or her first and fourth favorite object. So this allocation does not guarantee envy-freeness. So it's envy possible. Similarly, for the second allocation, it's possible that Bob might envy Anne. It all depends on whether or not Bob would prefer his third and fourth object to his first and fifth object. So both of these first 2 allocations are envy possible. It's possible or at least they don't guarantee envy-freeness. And finally, the last allocation you can check is in fact envy-free. Now, why is that? Well, Kath certainly does not envy Bob's allocation because 5 and 2 are strictly worse than the objects that Anne receives. Kath certainly doesn't envy Anne's allocation because 1 and 4 are strictly below her allocation. Does Bob envy Anne? Well, Anne receives 1 and 4, and both 1 and 4 are strictly below Bob's allocation. So Bob is not going to envy Anne. Now, what about Anne? Does Anne envy Bob? Let's look at Anne envying Bob. So Bob has object 2 and object 5. Both of those objects, Anne thinks to herself, well, object 5, well, I strictly prefer object 4, which is what I have, which is strictly better than 5. Looks at object 2, and she says, well, I strictly prefer object 1 over object 2. So Anne is not going to envy Bob, and similarly, it's easy to see that she's not going to envy Kath. So none of Anne, Bob, nor Kath envy each other. This is an envy-free division, and it's also efficient. However, we're going to see that this division does not satisfy a number of very natural properties. First of all, voting. Suppose that Anne, Bob, and Kath, they somehow determined the efficient divisions, and they now need to vote on those divisions. And the question is, will the voting method identify the envy-free division? Well, Anne's preferences over the divisions are going to be, she's going to be indifferent between A1 and A2. Those allocations give her both her top 2 choices. The last allocation, A3, gives her first and fourth choice. So she'll be indifferent between allocation 1 and allocation 2 and prefer those strictly to the last allocation, A3. Bob is strictly going to prefer allocation A1, where he gets his top 2 choices, to allocation A3, in which he gets his first and third choices, to allocation A2, in which he gets his first and fifth choice. And finally, Kath is going to be indifferent between A2 and A3, so A2 and A3, in which she gets her top 2 choices, and strictly prefer those to the allocation A1, where she gets her first and fourth choice. So now, given these preferences, we can ask what will happen under various voting methods. So note that by any pairwise comparison, A3 always comes out on the bottom. So A3 is going to lose to A1, and in a pairwise comparison, will vote A1 over A3 because she strictly prefers A1 over A3. Bob strictly prefers A1 over A3, and it's only Kath that strictly prefers A3 over A1. So in a pairwise comparison, A1 will beat A3. A2 will also beat A3. Note that Anne strictly prefers A2 to A3, and Kath strictly prefers A2 to A3. So both A1 and A2 will beat A3 in a pairwise comparison. How about approval voting? Well, approval voting, a natural assumption is that Anne will approve of her top 2 choices, Bob will approve of his top choice, and Kath will approve of her top 2 choices. And under that approval ballot, we see that A3 gets only 1 approval vote, but A1 and A2 are tied for the win. So under approval voting, A3 loses, A1 and A2 tie. Simple majority, A2 and A3 gets 1 vote, or plurality rather. A3 gets 1 vote, A2 gets 2 votes, and A1 gets 2 votes, similar to approval voting. The conclusion is the unique envy-free division would lose in a vote to any of the other efficient divisions. So if the 3 individuals got together and they needed to vote over these allocations, no voting method would actually select the envy-free allocation. But this just shows that voting may not be a good method to identify the envy-free allocation. It turns out that the envy-free allocation A3 does not maximize the total utility for all of the agents. Well, in order to even make sense of that statement, we have to somehow turn this preference ordering into a utility function. So how do we do that? Well, we're just going to borrow the idea of Borda. We're going to essentially use a modified Borda account. And what we're going to do is we're going to assign 6 points, or let's say a Borda score of 6, to the first-ranked candidates, a Borda score of 5 to the second-ranked candidates, 4 to the third-ranked, and so on, and 1 to the lowest-ranked candidate. Essentially, we're doing just Borda count, but we're adding 1 to each one of the scores. And then we can just calculate what is the total utility or the total Borda score assigned to each of these allocations. Well, let's look at allocation A1. In A1, Anne gets her top 2 choices, Bob gets his top 2 choices, and Kath gets her first and fourth choice. Adding up those scores, you get from Anne, she gets a Borda score of 11, Bob gets a Borda score of 11, and Kath gets a Borda score of 10. The sum of the utilities is 31. Let's look at the envy-free division. Anne gets 1 and 4, so she gets a Borda score of 9. Bob gets 5 and 2, objects 5 and 2, so he has a Borda score of 10. And Kath gets 6 and 5, so she has a Borda score of 11. Adding everything up, the total utility is 30. So the unique envy-free and efficient allocation does not have the highest overall utility or the highest overall Borda score. But there's another measure of social utility that we can use. And that's the Rawlsian or Maximin measure. So what we're going to do is we're going to look for each allocation, what is the minimal utility received by each individual. So Anne in allocation 1 receives her top 2 choices, so her lowest utility is 5, because the second object gets assigned the lowest utility. So the lowest Borda score is 5. Bob gets his top 2 choices, so his lowest Borda score is 5. And Kath gets 3 and 4, so her lowest Borda score is 3. For A2, the minimal Borda scores are 5, 2, and 5 for Anne, Bob, and Kath. So note 4 and 5 for Bob. 4 gets a score of 2, a Borda score of 2. And finally, A3, the Borda scores are 3, 4, and 5. So Anne's minimal Borda score is 3, Bob's minimal one is 4, and Kath's is 5. And so now, following the Rawlsian Maximin idea, we want to maximize the minimal values. Well, in this allocation, the worse off is Kath with a Borda score of 3, or a utility of 3. In this allocation, the worse off is Bob with a Borda score or utility of 2. And with this allocation, the worse off is Anne with a Borda score of 3. So A2 is out if we want to maximize the worse off in each of the allocations, so the minimal Borda score in each of the allocations. So how can we distinguish between A1 and A2? Well, we could use a lexicographic idea. We could say once we've taken care of the worse off, we can ask who is the second worse off. And in this case, Bob is the second worse off with a 4. And in A1, both Anne and Bob, the second worse off, receives a 5. So in order to maximize the second worse off, we should choose allocation A1, and the envy-free efficient division is again not chosen. So the conclusion here is that lexicographic Maximin will not select the unique envy-free division. So even when an efficient and envy-free division actually exist, it may not be possible to find it or identify it using well-known and well-studied measures of overall social welfare.